So, hello everyone, again I am here. So I will basically be presenting for our paper Temporal Resolution Analysis for Impact of Combined Temperature and Humidity Variations on a Photoacoustic Carbon Dioxide Sensor. So a brief overview of the agenda. So there will be a small overview, then a sensor assembly and measurement setup, then experiment setup, then I will tell about the machine learning models which we used and the studies we conducted, and finally I'll present the results and conclusion, and finally the future work. So now we want to, for this paper, essentially we want to study the environmental for photoacoustic sensor for doing the environmental monitoring. And essentially we want to find out what is the temporal response of the photoacoustic carbon dioxide sensor to combine temperature and humidity variations, not the a change in carbon dioxide concentration itself, but to the temperature and humidity variations. And the importance of studying this behavior is very useful because when we want to create such an offset machine, then we basically can use these machine learning models, for example, to offset that. And we conducted 4 studies with varying temporal resolutions. So maybe it may be confusing what temporal resolution essentially is. So it is basically the time window which we are using to observe the signal. So for the sensor assembly, it is like the last slide which I showed you. So again, on the left side, which we have is the photoacoustic sensor unit. And then we have this TO housing containing NTC ceramic base plate photodiode and a MEMS microphone, which is essentially sealed inside 100% carbon dioxide. On the right side, which you see is basically the block diagram of instrumentation and control workflow. So nitrogen and carbon dioxide are basically being mixed using the mass flow controller and then basically fed to a reference NDIR sensor, which is plus minus 30 ppm accurate. And then this is the outcoming gas is basically fed directly to a photoacoustic sensor, which is housed inside a temperature chamber, which basically contains the temperature and humidity sensors. So this time we concentrate on just varying the environmental conditions. So essentially the temperature and humidity variation. And we want to ascertain what kind of repeatable behavior does the photoacoustic sensor basically give us. And so for this, we basically go from an input range of 15 degree to 60 degrees Celsius in 12-hour runtime with a 30-minute time steps. And the relative humidity is basically also varying between 50% to 90% through a 12-hour runtime with 30-minute time steps. So this is what the experiment, for example, looks like. What you can look at the bottom. So we use 2 kind of machine learning models, essentially tree-based regression models and linear and regularized regression models. We use R2 score as a metric because we want to ascertain the repeatable behavior. So at what point our machine learning model has become some kind of, let's say, precise in predicting. Then for the features, we use delta temperature and delta humidity, the change in temperature and change in humidity. And also we, for separate experiments, we are trying to study the temperature and humidity exclusively as features. In in the upcoming slide, I will show what is the difference why we are using this. So we want to use the approach of basically having a comparative analysis of algorithms. And we use data normalization and noise filtering to basically ascertain our results. So for the study 1, what we wanted to do was basically study the temporal behavior itself. So we use the temperature and humidity change as input signal. And for this, we want to see whether the temperature and humidity signal produces exactly or similar behavior at a different time window. And for the second experiment, it is also same, but this time we are using temperature and humidity explicitly as input features. So this tells us basically that we can do 2 different kinds of studies, and based on this, we can find out what is better setup. And study 3 and study 4 is also very similar. This time we are trying to have this temporal resolution being combined over variable time. So that tells us that we take, for example, times the window of 1, 2, 3 till 100, 3600, and so on and so forth. So the time itself has become repeatable. So we shall be able to basically have machine learning model, which is able to give us the R2 score, or which is able to basically predict over a time horizon. That's why we add a different feature, which is the change in time itself. Similarly, for the study 4, we are given the temperature and humidity values as explicit feature with change in time as a variable feature, which basically is able to generalize over a series of time. So here are the results for study 1 and 2. On the left side, what you see is the temporal resolution. So it goes from 1 to basically 3600, and for the corresponding, we see the R2 scores. So we want to see whether the sensor's behavior has become repeatable. So for this, we basically take notice of what are R2 scores. So at whether the signal which we or the input which we are giving to the machine learning model is producing the same results as expected in the real-time setting. So at 700 seconds, we get 0.8245 R2 scores, and at 1200 seconds, we get a R2 score of 0.9248. And also for the same, we have a 3600 seconds, we have R2 score of 0.978. And one another thing which we carried out was basically studying the algorithm's behavior. So across all these temporal resolutions, we found out that cat-boost regressor basically is overperforming. So among all the temporal resolution which we fed in, this algorithm generally gave us the better result. And the temporal resolution, as you can see, at 700 seconds has become very repeatable. This is a good result, but as you compare it to the study 2, which essentially can be feed in temperature and humidity values as separate features, basically we are able to get an R2 score of 0.8188 really fast at 300 seconds. And at 1200 seconds, similarly, we get an R2 score of 0.9748. But this time, the top performing algorithm is an LGBM regressor. So this temporal resolution basically took into account only the temporal resolution which it was studying. So for example, 200 second time temporal resolution took the sampling time between 0 to 200 only. So there is no time basically being taken into account. But for study 3 and 4, as we will see, basically we take from the start, the temporal resolution from 1 to 3600 seconds. So it is trying to, let's say, approximate across the time resolutions. So it tells us that the sensor's behavior basically changes as the time resolution, temporal resolution, which is trying to analyze, is also increasing. So as you can see on the study 3, it starts at 0.9437, but it is due to the case that basically we are giving information from the higher temporal resolution as well. So at 1, as you see, it is 0.94, but after, let's say, 800, you are already at 0.95. So this is, let's say, the non-certain part of the temporal behavior which we see. But still, if we are trying to, let's say, regularize it or make it more predictable or generalize it, but it's for this horizon it is not, as you can see, but still it gives us overall a better response. At 3600 seconds, even the change in temperature and change in humidity as input gives us a decent R2 score of 0.9775. The top performing algorithm is random forest regressor for this. And for the study 4, and as you can directly notice, it starts at higher R2 score of 0.9811. And at 3600 seconds, basically it goes to 0.933. As you must have noticed that basically it starts at a higher R2 score. So that essentially tells us that feature engineering plays certainly a bigger part. And the performance is cat-boost regressor. For a layperson, it becomes not that interesting that we have these machine learning models, which are kind of black box. If we want to really see what's going on inside, let's say, these algorithms, so we can use something called as a linear regression model, which, for example, I'm just showing it for study 4. So for the R2 score of 0.8616, which is from 1 second onward, it starts significantly lower, but still it is able to give us a 0.8616 R2 score, and it is much more interpretable. So similarly, at R2 score of 0.9305 at 3600 seconds, we have R score of 0.9305. We can see that even the simpler algorithms basically can make such predictions. So corresponding equations for linear regression is there. So you can manually put in the values and get the results even you want to just have this behavior observed. And then similarly, there is the R2 score of 0.9305 at 3600 seconds because there is no higher time or temporal resolution being analyzed. So there is no temporal factor, the delta time factor is 0. In conclusion, we have the sensor of influence of temperature and humidity being studied, and the tree-based regression technologies basically give us better results. And also, this study can be used as a framework to analyze other kind of gas sensors. Thank you. We can do some future work. So future work is basically we can also conduct some kind of hyperparameter search for finding out the perfect balance between the accuracy and the model width or depth, for example, for regression models. Also, we can have sudden shift. So this time it was basically a 30-minute ramp. We can also give us like a gradual slope as well. And also we don't have at the moment any specific temporal resolution metric which we can use to analyze this. And thank you.